Rana fue la que se quedó a una.
Wow.
Entonces estaba buscando la estrella telúrica y militar. Oh.
Es de las peores excusas que he escuchado en mi vida. Llego tarde porque estaba buscando una estrella telúrica.
Para tener esas telúricas tienes que trabajar sin...
¿Lo has encontrado o no?
No.
Okay, thank you very much for being here. I think we can start already. Today we have Josep Tous, who is a visitor and is going to be here till
Tomorrow.
Okay. He did his physics studies in the Universitat of Barcelona and now is finishing his PhD. The defense is next 12th April, so this is going to be the test before the defense. And today he's going to talk us about the formation of S0 galaxies. So whenever you want.
Okay. Hello, everyone. First of all, I want to thank you, Pan and Elena, for inviting me to present today, and also for the nice introduction. So what I will present is a compilation of all the works that give shape to my PhD thesis, which is our collaborative effort to the understanding of these unique S0 galaxies. So, very good. This is the outline I will follow. First of all, I will talk about a bit the context and motivation behind my research. And then I will introduce the different classes of galaxies that we identify using SDSS single Fourier spectra. And I will talk about the physics behind our classification, which, as you will see, will be related to activity, but not only considering AGN, but other sources of ionization. And then I will present the extension of the whole methodology to the study of integral field spectroscopic data from MaNGA. Before moving on, let me mention that if you have any question, feel free to interrupt me. So let's begin answering a very basic question, which is why I am interested in these galaxies, S0 galaxies or lenticular galaxies. So look here, we have in the background some of these galaxies. Maybe you cannot appreciate the details from your chairs, but let me tell you that these S0 galaxies show intermediate characteristics between spiral and elliptical galaxies. Like the spirals, they are made of two structural components, a central bulge surrounded by a disk. However, this disk has no spiral arms. And like the ellipticals, they typically host red and old stellar populations and very little amounts of interstellar gas. And therefore, together with the ellipticals, they are considered as early type galaxies. But what really makes these galaxies so special is the fact that they are the only Hubble type that is relatively abundant in both low and high density environments. Instead, spiral galaxies are typically found isolated in the low density general field or as part of a small group, whereas elliptical galaxies are the dominant population within galaxy clusters. It is precisely because of this reason that more than one formation mechanism could explain the existence of these lenticular galaxies. But to tell you more about these formation mechanisms, let me go back in time to the first moment they appeared in the literature. S0 galaxies were introduced by Hubble as a hypothetical class connecting with intermediate characteristics connecting elliptical and spiral galaxies. Precisely, he put them just at the intersection of the different branches of the tuning fork diagram. In the beginning, some years later, S0 galaxies were associated with the lenticular galaxies that are frequently observed within galaxy clusters. At the beginning, it was thought that these galaxies came from direct collisions between the galaxies in the cluster, but later Gan and God showed that it is more likely that hydrodynamic interactions, such as the ram pressure stripping, give place to these S0 galaxies. You need to take into account that not even galaxy mergers work within galaxy clusters because the relative velocities at which galaxies move are much larger than the internal velocities of their stars. So in practice, two galaxies don't spend enough time together to feel the gravity of each other and eventually merge. So we think that lenticular galaxies in clusters could have been former spiral galaxies that have lost their interstellar gas upon falling into the cluster. It is the pressure exerted by the hot and dense intracluster medium what drives the morphological transformation. Once this pressure has removed the cold gas from the disk of these galaxies, the systems get hotter and thicker, and eventually the spiral arms fade away, giving place to an S0 galaxy. Perhaps the most strong evidence we have regarding the importance of clusters in driving the spiral to lenticular transformation is the well-known morphology density relationship discovered by Dressler in the 80s. This relation consists in the observation that in dynamically relaxed clusters, the fraction of a spiral plus irregular galaxies decreases at the same pace that the fraction of lenticular galaxies increases, with the logarithm of the local projected density. And we also have these beautiful images of the so-called jellyfish galaxies, which are only observed in galaxy clusters. These galaxies show these prominent tails that detach from their bodies, and this is the smoking gun of ram pressure stripping acting on these galaxies. Very good. We also have S0 galaxies in the low density field. And there, the mechanisms that work efficiently within galaxy clusters don't work because basically there is not enough intergalactic medium, to drive the sort of interactions, hydrodynamic interactions. And in addition, the velocity at which galaxies move are much smaller. So instead, we need to think of other mechanisms, and those that involve gravity are a good bet to explain lenticulars outside clusters. So we think that S0 galaxies outside large galaxy aggregations could come from mergers of galaxies, for example, between two coplanar spiral galaxies. A merger of such characteristics has the power to change the structure of the parent galaxies by triggering starbursts that hit the systems. And these, once there's no more gas available for fueling further star formation, the systems evolve. So the disks get thicker, it can grow a central bulge, and the spiral arms are destroyed. And therefore, we have an S0 galaxy as well. And we find evidence that supports this scenario through measures in several observational works. For instance, it is frequently observed among S0 galaxies that they show decoupled kinematic components. And this is illustrated here by these two maps, which show the velocity field of the stars in color and of the ionized gas of this S0 galaxy. You see that both maps don't match, okay? And this is really hard to explain without accounting for an external origin of this gas. Or we have this nice work by Mashman and company in which they report an overabundance of S0 galaxies in a sample of double peak spectra. Sorry, these S0 galaxies have star formation as well. Double peak spectra are thought to be the outcome of the final state of a merger between two galaxies. When the supermassive black holes are orbiting just before merging, they orbit at a velocity which is high enough in order to produce a spectrum with detectable multiple component emission lines. And not to mention that S0 galaxies are frequently obtained in merger simulations involving a wide variety of orbit configurations and gas contents. So maybe at this point of the presentation, you're beginning to suspect that such radically formation mechanisms should leave their unique input on the properties of these lenticular galaxies, and that this should be detectable, okay? Well, this has been the topic of research of several works shortly after the discovery of these lenticular galaxies. However, up to date, there is no clear agreement among the community regarding how S0 galaxies evolve. And this field is receiving a lot of attention lately thanks to the advent of the large spectroscopic surveys, which provides a fresh look to the problem from the perspective of the wealth of information contained within the spectra of these galaxies. So now I would like to share with you a couple of recent works that have used the spectroscopic data to identify a range in the properties of this population of galaxies, even some bimodalities that agree with this idea of being the outcome from more than one formation mechanism. So one example is this work by Elena and company, in which they identify a bimodality which is driven by the stellar mass. They find that while the low mass S0 galaxies from their sample show a strong metallicity radial gradient but null H gradient, the high mass S0 galaxies behave the other way around. They show a strong H gradient but very little or null metallicity gradient. Or there is this other work by Cocato et al., in which they apply a K-means algorithm on a sample of S0 galaxies on several properties, H, angular momentum, stellar mass, and so on. And they find obvious differences in many of the properties investigated between the two classes. And there are other works from different authors that have used different approaches, but they have reached similar conclusions. So what I want to stress is that it is really difficult to explain this heterogeneity in the properties of the same Hubble type without considering multiple formation mechanisms. So now let's talk about how we approach this problem. We use the full optical spectrum from a very large sample from the SDSS main legacy survey of about 70,000 nearby lenticular galaxies. The morphologies are taken from the neural network-based classification by Dominguez Sanchez et al. So in the very good thing of working with such a big numbers, apart from looking good, is that they allow us to work with volume-limited samples and therefore avoid all the kind of biases we deal when the samples are incomplete. So now I will present the highlights of this work, and here is the link in case some of you are interested or want to know more about the details. So let's talk about the spectral classification, but to explain it, I want you to visualize the problem we are facing. We work with the spectrum of the galaxies, and would you agree that the spectrum of a galaxy is unique, right? We could say it's like its fingerprint. It allows to distinguish this galaxy from the rest of the sample in a vector space where the coordinates of the vectors are the flux at different wavelengths. So if we were to consider, for example, H alpha, H beta, and sulfur, this galaxy would be placed in this subspace here, and this position depends on the flux at these three wavelengths, which in turn is a function of the stellar population of the galaxy and the gas content of this galaxy, right? A second galaxy with a slightly different baryonic content would be placed somewhere else, and yet a third galaxy, maybe with a stronger emission lines, could be even farther from the origin. So at the end of the day, when we represent the whole sample here, we obtain a cloud of data points, where the galaxies may cluster depending on common characteristics. For example, stellar mass, star formation rate, metallicity, and so on. So if the formation mechanism has left any imprint on any of these properties, this is here. So we should be able to identify it. Well, seems very easy, but it's not that easy because we need to consider that any new wavelength we add to the problem adds one extra dimension to the problem. And to give you a rough idea, an SDSS spectrum has 4,000 different wavelength elements. So at the end of the day, we will be looking at a cloud of 70,000 data points in a space of 4,000 dimensions. It's crazy. Well, in cases like this, we can apply a principal component analysis, and maybe, if we are lucky enough, we will see that some of these dimensions are linearly correlated. So in practice, we won't need all of them to obtain a good representation of the sample. A PCA is a diagonalization problem in which you have to find the eigenvectors of the variance matrix, and then you sort these eigenvectors in decreasing order of importance, and this gives you a new set of orthogonal axes, which are called the principal components, or since we deal with the spectra, we can call them eigenspectra as well. So in our case, these are the first three principal components together with the mean flux of our sample, and note that with just the first two, we explain almost 90% of the sample variance. So this ensures us that we can do a pretty good job classifying the galaxies in the subspace defined by these two axes. By definition, any spectrum can be expressed as a sum of the mean flux and a linear combination of m eigenspectra. And therefore, we can express the coefficients of this linear combination represent each of these spectrum. This is nothing else but the projection of our spectrum over any of these eigenspectra. So, with these few coefficients, the information of the spectra gets optimally summarized. And by picking just the first two, we obtain this friendly two-dimensional representation of our sample of data points. This is a very good thing about the PCA. Without any further effort here, we could already distinguish two different regimes, right? So accordingly, we applied a logistic regression. This is a binary classifier that returns an extremely bimodal probability distribution function of belonging to either of the two classes. And to it, we can apply Otsu's method and maximize the interclass variance. And by picking the value of 95% of the interclass variance, we have our objective definition of different spectral classes. Then, having a look into the typical spectrum of the galaxies in each of these different classes, we see that all the galaxies that sit in this narrow and densely populated diagonal band show all passive spectra that are dominated by absorption lines. This corresponds to a 70% of the local S0 galaxies. Then, another 25% of the local lenticulars show active spectra, and the strength of the emission lines of these spectra increase the farther we move away from this passive region. This is illustrated here with a color map of equivalent width in the H-alpha line. And the very few objects in the middle with intermediate spectral characteristics, we say that they are in a kind of transition region. So we will use any of these names to refer to all these classes. Then, doing a bit of demographics, we observe that in comparison to the passive population, the active population of S0 galaxies is slightly less massive, but this difference is statistically significant. Then, they typically host bluer, younger, and less metal-rich stellar populations, and this is maybe the most remarkable result. They show specific star formation rates that can be as high as those observed in Milky Way-like galaxies. We are talking about early-type galaxies, okay? And finally, these active galaxies avoid high local densities. This is illustrated here by the steady decrease in the fraction of the active population as a function of our own local density estimate. This takes into consideration the average to the 5 nearest neighbors. The color scales with the equivalent width of the H-alpha emission line, and the size of the dots is proportional to the average star formation rate of the galaxies in two. Very good. The discovery of an active class of S0 galaxies motivated this second work. This is a detailed study of activity at several wavelengths. However, today I will focus mainly on the optical part, as it would take me too long to go through each of the wavelength domains and give you all the details. Activity, again, considering not only AGN, but also star formation and other sources of ionization. And just to mention that the backbone of the study in the optical part is the good correspondence between the equivalent width of the H-alpha line and the distance from the passive sequence of any spectrum in this plane. This distance is nothing else but the orthogonal distance to this line, which is a fit to the galaxies in the passive sequence, right? And it's given by this expression here. So to understand why things are sorted the way they are and where does this activity come from, we can compare our parameter delta PS with well-known scaling laws. For example, the main sequence of the star-forming galaxies. If someone is not familiar with this main sequence, this is nothing else but the linear relationship that exists between the star formation rate and the stellar mass of star-forming galaxies in the universe. The deviation from this main sequence, expressed like this, is nothing else but a fancy way of saying specific star formation rate. So here it is, distance to the passive sequence, or in other words, activity, in something like general, versus distance to the main sequence or specific star formation rate for our sample. Here we have binned all the data points into hexagonal cells, where darker tones imply larger density of data points, and these horizontal dividers correspond to our spectral classification in terms of delta PS. And these vertical dividers are a quite standard definition of the different regimes along this parameter. Here we have quiescent galaxies, galaxies on the green valley with intermediate specific star formation rates. This is the main sequence, and here we have some starburst galaxies. So this is telling us that while the passive population is essentially made by quiescent galaxies, the active population sits actually on the main sequence. So the active spectra is not only the outcome of AGN. We have galaxies with a healthy star formation in the active population. And one last result that comes out from this plot is that there is a tight correlation between our parameter delta PS and the specific star formation rate of the galaxies. So in practice, one can be used as a proxy of the other. This is really convenient for us. Then to disentangle star formation from AGN, we can compare our classification with the outcomes of a BPT standard diagram. So first of all, the very few objects on the passive sequence with a strong enough nebular emission to be considered in a BPT, they are essentially liner galaxies, whereas for the active population, we see that there is a mixing of star formation and AGN, although it seems that star-forming galaxies outnumber the safer galaxies. And this is confirmed going to the radio domain or the X-ray domain. This is a very simple test. Consists on drawing the histograms of luminosity at 1.4 gigahertz from the first survey, or the broadband luminosity in the X-ray from the 4XMM catalog. And by picking a value of 10 to the 23 or 10 to the 41, this allows you to distinguish when the luminosity is dominated by the star formation or by AGN. And you see that for most of our sample, the luminosity is dominated by a star formation. Okay, but since we are dealing with early type galaxies and we've seen that the bulk of our S0 galaxies have passive spectrum, maybe a more suitable diagram to characterize activity or more inclusive is the one diagram. That is the equivalent width of the H-alpha line versus the ratio of fluxes nitrogen over H-alpha, and here the color scales with our parameter delta PS. As you see, it goes with the y-axis of this diagram. And here we have on the right-hand side of the screen the same diagram, but now I am showing in contours the distribution of our spectral classes. Let me stress that this is one of my favorite results from Jimenez Palau and company, because it shows a remarkable coincidence between the spectral classes and the dividers of the one diagram, especially with the horizontal ones. And again, this is remarkable because these dividers come from theoretical predictions, from models that predict which are the thresholds of emission at these wavelengths coming from star formation, from AGN or post-AGN stars, whereas our classification arises purely from mathematical arguments. So indeed, the one is giving us the physics behind our classification. We have a classification of activity that makes sense. And now a little spoiler. If we incorporate to our classification the third principal component, we can now characterize activity in any galaxy regardless of its intensity. And this is so because instead of relying on just a few emission lines, like the VPT or the one diagram, the principal components rely on the flux from the whole spectrum, optical spectrum. So this is here, I'm showing with different markers the outcomes of VPT classification. This is the outcome of the one classification, and this is an updated version of our PCA classification, where now we can distinguish the source of activity for the active population. And Sí, espera. Ahora yo tengo que hacer. Sí.
HDMI está conectado. Vale.
En teoría.
Entonces, si le digo.
Ahora.
Okay.
Vale.
Sorry for the interruption.
Okay.
You have extra time.
Thank you. Likewise, I will try to run a little bit. Okay. So, going back to Elena's comment, yes, it helps to consider outside-in quenching, inside-out quenching, and that's also the reason why I put this map always that I'm talking about some configuration or another. Okay, so we've seen that the spectral class and the activity gradient are related. Also, in terms of specific star formation rate, we see interesting trends. We see that most of the galaxies on the main sequence have this type of maps or an outside-in activity configuration. Galaxies on the green valley typically show inside-out activity profiles with this configuration, whereas the galaxies on the quiescence region have a low-level flat activity profiles. And then finally, in terms of the VPT class, the things show this relation. Seyfert and star-forming galaxies typically have an outside-in activity profile of this type, whereas the liners concentrate the other two activity configurations. So now we may wonder which are the mechanisms that are able to produce these activity configurations in the galaxies. So one possibility for the outside-in activity configuration is RAM pressure stripping. Here I am showing you a simulated spiral galaxy undergoing RAM pressure stripping. The wind is coming from this direction. This shows the surface density of different gas components, and the cyan contours show the extent of the stellar disk. As you see, this looks very similar to what we see in the maps of the S0 galaxies with this configuration. But RAM pressure stripping removes the gas from the galaxies on a relatively short timescale. So this reduces the chances of observing an object just in the middle of this process. Besides, the RAM pressure stripping is even more dramatic with low mass galaxies. And these are most of the galaxies with this activity configuration. This is shown here by the light brown histogram, which shows the cumulative frequency of the subset of galaxies with this activity configuration in comparison to the other activity configurations. And this here indicates the median for this subset on the stellar mass, which is around 10 to the 10, and it can be even lower if we were considering only the subset of these galaxies that are star forming. As I've showed you, these are the majority with this activity configuration. So we find more compelling an scenario that has been discussed recently on the literature to explain these galaxies, especially the low mass, which would be that this configuration is given by a central enhancement of a star formation as a result of a minor merger. In addition, we find that the galaxies with this configuration show characteristics which are very similar to those of the S0s that Rathore et al. Identify as potential candidates to have been rejuvenated by a minor merger. They say so because they identify on their sample of S0 galaxies a lot of kinematic decoupling. Okay. Then the inside-out activity configuration we have already discussed that is closely linked to the presence of star-forming rings, and we have discussed mini-mergers as a possible explanation for these disk instabilities. So we will use the mini-merger scenario to explain, if not all, most of the galaxies with this activity configuration, because they show characteristics favorable to this sort of disk instabilities. Most of them, or many of them, belong to the passive sequence, are globally passive, and many of them have a rather large stellar mass. This is indicated by this box plot here in orange that shows a summary of the PDF of the stellar mass for these galaxies in 3 bins of local density, from lower to higher local densities. And in addition, we see that galaxies with this configuration are found almost at any kind of environment. And finally, no matter which is the mechanism, that once this activity disappears, if there are no further rejuvenation events, the galaxies will develop a low-level flat activity profile because activity will disappear across the entire galaxy. This fits with the idea that this activity configuration is the most popular among S0 galaxies, and also this is supported by the range of masses and environments that we find in the galaxies of this subset. But maybe the picture that best illustrates this flat configuration as the finish line where sooner or later S0 galaxies arrive is given by this diagram. This is the distribution in the plane of angular momentum versus ellipticity of 2 subsets of our sample of lenticulars. That is for the star-forming galaxies with an outside-in activity profile, and this is for all the galaxies with a flat activity profile. The dashed line corresponds for, it is a guideline for regular rotators that are isotropic seen edge-on, while the solid line are for an anisotropic rotator. This comes from theoretical models, whereas this box here identifies where the slow rotators are, which in our sample are very few. So we compare these 2 distributions with a kernel density estimate, and here we see that for the outside-in subset, this fits with this scenario of minor measure rejuvenation. This is indicated here by a larger pressure support of the systems and a smaller ellipticity than the flat subset. These diagrams give you an idea of the anisotropy in the shape, but also in the velocity field of the system. So this is in line with the idea that mergers contribute to heat the systems. Whereas the flat subset shows this bimodality, which could be the outcome of 2 different formation mechanisms. The peak on the left-hand side could be for lenticulars that, like those of the outside-in subset, have experienced some mergers along their lifespans, whereas the peak on the right-hand side of this diagram could be made by all the S0 galaxies that, after acquiring their lenticular shape, have had a more boring life without experiencing alterations in their shapes or the velocity field. And one last result I want to show you is that if we repeat the same exercise for the subset of Seyfert galaxies, we find that Seyfert show a larger rotational support than average. This is indicated here. The angular momentum of these galaxies is much larger, and this is in agreement with some works on the literature. So I think we can leave it here. I'm gonna leave. This is the list of things I would like you to take home with you. And now, if you have any question, I will be very happy to answer.
Very nice talk. Questions? Yes.
Many of them. Try to be brief. Thank you so much. Very nice talk. I have a couple of questions, but so let's stick with the first one. You're suggesting that then mostly all the activity that you observe is due to mergers, either minor, mini, or...
Exactly.
Okay. There are some predictions about the specific amount of mergers that you will expect for a galaxy at a given redshift, depending on the environment and so on. So my question would be whether you have checked if your findings in the numbers of lenticulars with this characteristic fit well, like match more or less with the prediction of the amount of galaxies that you expect have suffered from a recent merger. Because if you see this, it's because the merger it's recent, right?
No, we haven't checked that. Okay. In principle, as I say here, we are obtaining that mergers play a very important role in the evolution of these galaxies. No matter which is the configuration of activity, but every time we observe activity, it is probably, or we think it's probably, because it's given by a merger. So they have to be quite common, but we haven't contrasted this with theoretical predictions. So that would be something interesting to look at.
Okay, thanks. Yeah. Let some other ask more questions.
Yeah, thanks for the presentation. Very interesting work. You mentioned that the rings are twice more likely to appear in passive galaxies.
Yes.
So could this be a detectability issue, that it is more difficult to see the ring when the whole disk is forming stars?
Yeah, that's something we when we were doing this paper, we wondered ourselves. However, we are also finding rings in active galaxies. Okay, so we, in addition, are using. We played with the scales of the intensity we were representing on the maps to see if it was a problem of contrast or something like this. And we didn't find anything that made us suspect that we had this kind of problem. And in addition, we found in the literature some results that agree with this result, that they are more common in globally passive zero galaxies. So yes, we had that in mind, but we ruled that out.
Okay.
On that moment.
Carol?
Yeah, well, it was more or less in the same line as previous questions. So I was thinking about the outside-in quenching, and I was wondering whether, in addition to mergers, there could be internal mechanisms to drive this quenching effect. I don't know. For instance, if you have bars, or if you have some mechanism that drives gas
to the center,
and since you are using H alpha, which traces very short, long time scales, perhaps it could be interesting to extend this analysis to different wavelengths, tracing more
a larger scale. Yeah. Okay, so we know that we are not, in this case, we are not thinking about quenching, it's more about rejuvenation, okay? Because we are saying that this is an enhancement of the star formation rather than quenching. So the thing is that we are observing a very high intensity on the central part of the galaxy. And I don't know if circular mechanisms like maybe bar formation or inflows could give such a large emission on the H alpha. I don't know. And it is true that we are dealing with H alpha, which traces a very short time scale for that. And we indeed, one of the plots I was showing you reflects very well what you were commenting here. Sorry. Yeah, here, as you see, we have some galaxies on the passive sequence that are on the main sequence, so they have current star formation, okay, and very few of them on the starburst zone, okay. But this is because this delta main sequence, this star formation rate and this stellar mass come from multi-set fitting, okay, from an external catalog, and this is telling us that we have this sort of problem, that we trace a very short time scale of the star formation processes. But yeah.
Hector?
So if every wavelength is used in the input intensifier, has every spectrum been equal to rest frame?
Yes. I skipped that part, but yes, all the spectrum are shifted to the rest frame and normalized to a similar continuum.
So could this cause any problems with the emission lines, or are they smooth in some way?
With the emission lines, you mean, for example, H alpha or?
Yeah, like the resampling.
Yeah. Indeed, we are interpolating to rescale to a different binning. So yes, this could be giving us a bit of problems, but in principle, it should work with this.
What happens if you have now another sample with a different wavelength coverage? So if you are missing some part of the blue or some part of the red, does it changes the classification somehow, or?
Yeah, this is a very interesting question.
To compare with data,
Yeah.
higher resids or maybe from different spectra.
This is on one of our short-term goals, to extend this kind of classification to other morphologies, but also to other kind of data. I think the main problem is with the resolution, okay, but we can always lower down the resolution or do these sort of things. But then if we are missing some information, we have done some tests in which we remove some parts of the spectra. They are not very large parts, so maybe we should be more exigent in this way, but it works. Okay, so if we remove the whole blue part, I don't know what would happen.
Yeah, at some point.
Yeah. But this is on my to-do list, also to remove, for example, H alpha, which plays a very important role in the classification, and see what happens, and also to play with the signal to noise ratio of the spectra and see how the classification operates. But yeah.
And how do you treat the extinction? Do you correct the spectral extinction, or it's folded in one of the principal components?
We correct for galactic extinction, but not for internal extinction of the galaxies. And this is something that worried us on the first paper. We fight a bit with the referee, but in the end, well, I cannot move from one side to the other again, but never mind. We saw that the effect of extinction, we assessed that with the inclusion of galaxies, only played moving galaxies parallel to the passive sequence. So they didn't change the class. So in this sense, we are kind of safe. Yeah, that was maybe a lack, but it works.
Okay. More questions? Carlilla? Unless you want to follow up, please.
I was gonna say that the main difference between the two first principal components was that one had a red continuum and one was a blue continuum.
Yeah, that's right. I forgot to mention if this is encoded on the principal components. But one thing is that one is red continuum, the other is blue. So this, in the end, makes that it goes parallel to this passive sequence. And also further higher order components like PC3, they are essentially flat with emission lines. So there, the continuum is not playing at all.
Okay. So thank you very much for the very nice talk, very illustrative. So in the first word, you were using Sloan spectra.
Yeah.
So you are looking just to the center of the galaxy because the velocity is relatively low. I don't know if that can. So
yes,
the first results are for the center.
Yes.
Central part.
Yes. This is together with the extinction. The other thing we were fighting with the referee. Yeah.
We were not the referee.
No.
No.
It's good that you bring that up. Yes. But again, we assessed playing with different. How we did that? We assessed the ratio of the apparent aperture of the fiber with respect to the effective radius of the galaxy, and we played with that. And we saw our conclusion was at the end that we were also seeing a bit of the disk. And also thanks to the inclination that when we have an edge-on galaxy, we have the disk just in the middle of the fiber, we were tracing somehow as well the disk of the galaxies. And another proof is that when we extended the whole methodology to MaNGA data, we found very similar principal components. And this is on my backup slides. Yeah, this is the comparison. These work are the principal components. This is MaNGA components, okay, using the radial stats, the mean flux. And in red are the residuals of subtracting this flux to the flux of the Sloan spectra. And as you see, the residuals here are really, really low. Okay, and then we did further tests to express one component as a function of the others, and we found that the matrix we obtained was very similar to the identity. So they are really similar. And in MaNGA, we are tracing the disk or part of the disk.
There's another question. Just now in the MaNGA, you are saying that they're playing with the gradients, but also you have the global classifications.
Yeah.
And the global classification is from the center. Is
from the Sloan. Is from the Sloan. Yes, I forgot to say that on the presentation. Yeah, when we say globally passive, globally active, it's from the Sloan. But one other result of this last work that it's not on this presentation is that normally when we say that a galaxy is globally active, its whole radial profile is contained in the active cloud. The profile. So the classification, the single fiber classification normally agrees with the profile in delta PS.
More questions? I sense something over there.
Perhaps. Can you go to the slide where you show the angular momentum versus ellipticity?
Yeah.
Okay, that one. And then you also had the same, right? All right. So
yeah,
I didn't get exactly what were the two clouds that you observe on the flat profile. So these are clearly more pressure supported, and what's the origin?
Yeah, sorry, maybe I rushed a bit. So yeah, so here the idea is electricity, again, angular momentum. Okay, so when here we have rounder systems, and here more elongated systems. So this is a bit more pressure supported because the angular momentum is smaller. Okay, and then these 2 points, they have essentially the same angular momentum, but in terms of ellipticity are slightly different. So mergers contribute to make rounder objects, whereas if these galaxies have not experienced so much mergers, they will be more flattened. They will be disks, more prototypical of the spiral galaxies, for example. That's the idea. That's the idea. And this is even more clear with the safer galaxies, which are more or less upwards here, but with much more rotational support. So these are healthy disk galaxies. And this points to a relation between the angular momentum and the feeding of the supermassive black hole.
Okay, got it. Thanks.
Okay, there are no more questions. Thank you very much again. Where is Mist?
Sí, sí.